Hello friends, welcome to weekly lectures. In this lecture, we are continuing the digital circuits. We will first look into subtractor, the different kinds that are half subtractor and full subtractors. Then comparators, 1-bit comparator and 2-bit comparators. Similar to the adders or the addition operator, we have the subtractors, which perform the subtraction of n number of 1-bit number. Now there are two kinds of subtractor. One is half subtractor and the full subtractor. For half subtraction you have two 1-bit number. For full subtraction you have three 1-bit number. Anything similar to the adders. Now for half subtraction you have two input A, B, and the D and B. This is the difference terminal or the difference output. B is the borrow. Borrow means whenever you have, for example, 64 minus 35, you have to 4 minus 5, which is not possible, so we take one from the 6, the neighboring one. So 14 minus 5, that is 9. So here you borrow 1, that is called borrow. So here borrow is equal to 1. Okay, so borrowing, the actual value of the borrowing is 10. You are buying 10 from here because 4 plus 10 is 14. 14 minus 5 is 9. So now what is left? 5 minus 3, 2. Okay, so here, but in the case of 2-bit number, your borrow value and the difference value will be always 0 or 1. So the difference is A minus B, and borrow will happen only when A is less than B. If A is less than B, then there is borrow. So borrow will happen. So what are the values of borrow? There are two cases, A less than B or A greater than B. You are seeing borrow, you are doing A minus B. If A is less than B, borrow equal to 1. If A is greater than B, borrow value equal to 0. Similarly, for full subtractor, you have three input terminal A, B, C, and this is difference, and the output B stands for borrow. Now what is A, B, C for a full subtractor? This means A minus B minus C. So first you have to do A minus B, then minus C. This is the difference. And what about borrow? B-O-R-R-O-W. Now in this case, if A less than B or B less than C, if either A should be less than B or B should be less than C, then your borrow value equal to 1. Otherwise, borrow value equal to 0. These are the things that you have to remember when moving forward with half subtractor and full subtractor. Now let us see for 2-bit and 3-bit numbers how this subtractor behaves. That is for half subtractor, and the full subtractor. So here is the half subtractor, where there are two inputs, A and B are the input, D and B, let's write borrow just to avoid the confusion, are the output terminal, which is the difference and the borrow. So difference, you write borrow one slash. Okay, so 0 0, what is the difference between 0 0, or 0 minus 0 is 0, so actual difference you can write 0 and 1, difference is 1, 1 0, difference is 1, 1 and 1, difference is 0. Now what about the borrow? 0 and 0, there is no need to borrow. 0 1, yes, 0 minus 1 means you have to borrow from the other, so which is A is less than B, so there is borrow. Here A is greater than B, so there is no need of borrowing. 1 and 1, no need of borrowing. So that's it. Now you have two output with respect to the output D and B. You can create, that is the difference and the borrow, you can construct the K-map. You have already constructed the truth table here. Now this is the K-map corresponding to the difference. So wherever there is 1, so make it, so this is 0 0 1 1 1 0 2 1 1 3, so this is 0 1 2 3, so difference 1 and 2, 1 and 2. Here you have 0, this is 0, so 1 and 2 means A bar B, so difference is equal to A bar B plus this is AB bar, AB bar, right? So you can write it as A XOR B. So difference D is can be developed or constructed using XOR gate. Now coming to the borrow, there is only one borrowing, where it is 0 1 0 1, that is 1. So here 0 1 is 1, right? So this is 0, this is 1, this is 2, this is 3. So at 1, so all others are 0 for a borrow output, which means A bar B. So the borrow output B dash, that is called, is equal to A bar B. Here we have the digital circuit corresponding to the digital circuit corresponding to half subtractor. Half subtractor, and this half subtractor, we have the difference which is given by A XOR B, that is the XOR gate, and the borrow B dash given by A bar B. Okay, so AB going to the XOR gate and giving the difference as A XOR B, and the next B dash, which is nothing but A bar B. So A goes to the negation operator or the not operator, becomes A bar here, and this is B, which gives us A bar B. So in general, the half adder circuit y is equal to y borrow, sorry, difference plus y borrow, which is equal to ax or b. That is the first output. Second output, there is no need of plus. It consists of two output, comma a bar b. So this is the second output. This is the truth table, the first one, truth table for full subtractor, and what is the full subtractor? Difference says difference is equal to a minus b minus c, and for borrow you should know whether there is a possibility of borrowing till the end. Usually you can consider if a is greater than, sorry, a is less than b, or b is less than c. Okay, but there can be conditions where this is not valid, but in general you can consider this. Let us do this, the truth table. You can understand a minus b minus c, 0 minus 0 minus 0, so 0. Is there any borrowing required? I have not borrowed from anywhere. Then 0 minus 0, 0. 0 minus 1, yes, there is a difference, 1. And what about borrowing? Since 0 minus 1, I am subtracting from a lower value, so I have to borrow. Here also 0 minus 1, I have to borrow. So here 1 is the difference. Yes, there is a borrowing. Yes. Now 0 1 1, 0 1 1, the difference is 0, but I have to borrow because 0 minus 1, so there is a borrow. Then what about this 1 0 0, 1 0, 1 minus 0 0, 0 minus 0 0, I mean 1 minus 0 minus 0, so 1 is the difference. There is no need of borrowing, so it is 0. Then 1 0 1, from 1 to 1, okay, fine, 1 minus 0 is 1. Then again minus 1, which is 0. And what about borrow? There is no borrow. 1 and 1, the difference is 0. Again there is no need of borrowing. And what about here? 1 1 and 1, 1 minus 1 is 0, 0 minus 1, so there is a difference, as well as there is a borrow, because 1 minus 1 is 0, 0 minus 1, you are subtracting from a lesser value, so there is a requirement of borrowing. Then according to this thing, you can mark the values 0 1 2 3 4 5 6 and 7. Now for difference, this is the difference k map for difference. So you have 1 2 4 and 7, 1 2 4 and 7. Now let us write down the corresponding SOP. So a bar, this one, first one, 1, a bar b bar c, b bar c plus a bar b c bar, a bar b c bar plus ABC bar plus AB bar C bar plus ABC. Simplifying, A bar into B bar C plus BC bar plus A into B bar C bar plus BC. This is A bar into B XOR C plus this is A into B XNOR C. So this we can write it as A bar into B XOR C plus A into B XOR C whole bar. So together we can write it as A XOR B XOR C, because consider this it as A bar X plus AX bar. A bar X plus AX bar. This is equal to A XOR X. So this is the difference, and you could if you remember the truth table or the final expression for the sum in the full full adder, you will also see that it is equal to sum is equal to A XOR B XOR C, because addition and subtraction are in general the same thing for a 2-bit number. Coming to the K-map for the borrow, this is the borrow truth table. 0 1, so this is 0 1 2 3 4 5 6 7, so corresponding to 1 2 3 and 7, 1 2 and 3 and 7, you have the higher input. And now let us try combining. So here we have the first group, this is the second group, and here you have the third group. So first group says let us write down the borrow itself. In general, borrow is equal to A bar is common, BC bar and BC is left, so B bar C and BC, so B bar gets cancelled, C will remain, so it is A bar C plus the second one A bar, BC and BC bar, C bar will go, so AB will remain, AB plus in the this one BC would remain, A bar would go, so that is BC. So borrow is equal to this is A bar only, A bar B, A bar here, A bar is remaining, BC and BC bar, C bar will go, B will remain, so A bar B. So B dash or the borrow is equal to A bar B plus A bar C plus BC. So this is the borrow for the full subtractor. Now let us construct the digital circuit. So this is the digital circuit using the logic gates for what? For the full subtractor. and where the difference in the full subtractor is given by A X or B X or C, and the borrowing is given by output is given by A bar B plus A bar C plus BC. Now this is A, B and C all are going through the XOR gate, producing the YD difference, and in this this is C and B, so BC. So here you have BC, here you have A which is going through the NOT gate producing A bar, and B, so this is AND gate, here again AND gate, this is again AND gate. So A bar B and this is A bar C, then all are moving to OR gate. So in general what it became finally you have A bar B plus A bar C plus BC. So this is the output of the borrowing, so YB. Okay, so that's it. Comparators are a device or the logic circuit used for comparing two n-bit number. Usually we consider here 2-bit number, but in general it is for an n-bit number. What we compare the values of two input, that is, if there is two input A and B, what the comparator do is it will check whether A is less than B, or A is equal to B, or A is greater than B. So this is these are the only three options or available, right? If you are given two bits or two numbers, either A will be less than B, or A will be equal to B, or A will be greater than B. Now what does the comparator do if A is less than B? So here you have three output. So three output, let us say Y A less than B. That means the output Y where A is less than B, output Y where A equal to B, and output Y where A greater than B. Now for A less than B, you have to write what this is Y, this is another Y, so A less than B. Now check whether A is less than B. Here no, A is not less than B. Here yes, A is less than B. Here no, A is greater. Here no. Is A equal to B? Yes, A equal to B in two situations, when both are zeros and both are 1. In all other cases it is not possible. Now what about A greater than B? Yes, here it is not greater than, here also it is not greater. Yes, here A is greater than B, and in the last case A is not greater. So now you got the truth table for all Y's. Here A equal to B, here A greater than B. Now the step, that means the next step is to find the K-map or reduce the expression, reduce our given expression using the truth table. K-map is for reducing the expression, and after reducing the expression, what will do? You find the logic circuit corresponding to the different output. So here we have the truth table here. So a less than b, where is a less than b? So this is not, here a is less than b, here no, no. Equal to b, a equal to b in two cases, here and here, these two cases not equal. A greater than b, only one conditions, all others 0. Now this is a 0, 1, 2 and 3. So 0, 1, 2 and 3. So here a less than b, a less than b is only for here 1. In this case a less than b. So what is a less than b output? Output will be a bar b. So a bar b. A greater than b, a greater than b is here, where 2. 0, 1, 2, 3. 2 is here, that is a b bar. So this corresponds to a b bar. Now a equal to b, this condition, that is 0 and 3. So 0, 1, 2, 3. 0 and 3. In 0 and 3, in these conditions, it is output is 0. 0 and 3, 1 and 1. So that is a bar b bar plus a b, that is equal to a XNOR b. So you need an XNOR output, then 2 AND gate, which gives us the entire output. Now let us draw the logic gate a and b to the XOR gate. Sorry, it is XNOR gate, because you have NOT gate in front. This is not. So here this is y a equal to b. So XNOR gate gives you y a equal to b. Then a bar b, this is y a less than b. So what is this? This is a XNOR b. And what about this? Y a less than b. Less than b is here, a bar b. A bar b, what is the corresponding logic gates? A bar is here, this is the NOT gate. Again, this is NOT gate here. So NOT gate, this is a bar, and this is b, and this is the AND gate, which gives us a bar b, and this is NOT gate from a, and this is b bar, because this is b. So this is again AND gate, which gives us a b bar. So this is the comparator for a equal to b, a less than b, and a greater than b. Here is a 2-bit comparator. Now what is it, the difference between 1-bit comparator and the 2-bit comparator? Here each terminal or each input is a 2-bit number. Here you consider a as equal to a0 a1, that means it can be 0 1 1 1 or 1 0, anything. So it is a 2-bit. Earlier a equal to 0 or 1, but here a will have different combinations, 0 0 0 1 1 1 1 0. These are the 4 combinations. Okay, similarly for b, in the beginning we had only 0 1 for a 1-bit comparator, but now b is made of b0 b1, so it will have 4 combinations. So b is equal to 0 0 0 1 1 0 and 1 1, just like a. So that is the main difference. Here you will have 2-bit in the input side. Okay, not 2-bit number, it is 2 bits together. Okay, now we have to check for a less than b, a equal to b and a greater than b. These are the things that a 2-bit comparator compares, just like every other comparator. Now let us see what are the truth table and corresponding output of this 2-bit comparator. So this is the truth table, a very big truth table we have. So let's start numbering: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. See, this is the decimal number, and corresponding to this decimal number, this 4 bits represent binary number. Okay, so 0 corresponds to 0, 0, 0, 0. 15 means 1, 1, 1, 1. 3 means 0, 0, 1, 1. Okay. Now, if a greater than b, a equal to b, a less than b. So these are the 3 conditions that we have. Now let us look into the first one, a not a1. So this is 0, 0 and 0, 0. Where does it go? It go 0, 0 means 0. So it goes to a equal to b. Right. Now 0, 0, 0, 1. B is greater. So this is b. Together it is b. So b is greater. Yeah. So b is greater. Here also b will be greater. Here again b is greater. Here b is less than. So here this is a is greater. 0, 1, 0, 1. So both are same. 0, 1 and 1, 0. In this b is greater. And 0, 1, 1, 1. Again b is greater. Again 1, 0, 0, 0. 1, 0 is greater. So a is greater. 1, 0, 0, 1. In this case again a is greater. 1, 0, 1, 0. Both are same. 1, 0, 1, 1. Yes, in this b is greater. 1, 1, 0, 0. Which is greater? A is greater. 1, 1, 0, 1. Again a is greater. 1, 1, 1, 0. Again a is greater. 1, 1, 1, 1. But here both are equal. Okay, so a greater than b for 8, 9, 12, 13, 14. That is a greater than b. Okay, now our truth table is completed the truth table. Now we need to write or do the k-map for a greater than b, a equal to b and a less than b. This is the k-map, for a less than b. So a less than b. From the truth table, take out all a where less than b, all a where it is less than b. So it's 1, then 3, 2, again 7, 6, apart from that 11. In all these cases we have a less than b. Now after making the k-map, now try to draw the make the group. So this is one quad, one quad pair, and another pair you can get from here, this one and here. So finally what does it gives? Let us start with the pair 1 gives here b0 bar b1, b0 b1, so b0 will go, b1 will remain. Here a0 bar a1 will remain, so a0 bar a1 and b1, that is the first pair gives. Second pair is here, so in this column b0 b1 will remain, a0 bar a1 is here, a0 bar a0 a1 bar, so here a0 bar and a0, that a0 and a0 bar will go, a1 bar will remain, so plus a1 bar b0 b1, so b0 b1. And now we have this quad. In this quad, two inputs will go, that is b0 b1, b0 b1 bar, so b0 will remain, here a0 bar will remain, a1 bar and a1 will go, so a0 bar will remain, here b01 b0 b1 bar, so b0 will remain, so b0. So this is for the Y output where A is less than B. So just the output. Now coming A equal to B. Now this is for the K map for A equal to B, and for A equal to B, all A say 0 5 then 15 and finally 10. So these are the places where what you have the A equal to B. So let us write down. So there is nothing to remove, everything is as it is. A0 bar A1, B0 bar B, sorry, A0 bar A1 bar, A1 bar, B0 bar B1 bar, plus the second term A0 bar A1, B0 bar B1, plus this is A0 A1. So A0 A1, same similar, B0 B1 again, plus here A0 A1 bar, so A0 A1 bar, so the second term should be same, B0 B1 bar. So this is the output for A equal to B. Again we have A greater than B. So A greater than B in all other cases, like we have 1 4 this 13 9 and one more, that is 14. Now we need to group grouping can be done like this. So this is the first pair, and second pair we will take like this, and next we have a quad we will do with some other color, and this is the quad. So pair 1 uh, b0 b1 will remain, a0 bar and a0 will go, so a1 b0 bar b1, so a1 b0 bar b1 plus another pair is a0 a1, and the one we will miss is b0 bar b0, so b0 bar b1 b0 will go, so b1 bar will remain, so a0 a1 b1 bar, so a0 a1, and what is remaining, b1 bar plus, now let us take the quad a0 will remain here, and in this b0 bar will remain, so b0 bar, the common will remain. See what is the common here, b0 bar, and here also b0 bar, so b0 bar b0 bar, but b1 bar is there, b1 is there opposite, so that will go, so b0 bar remains. What about a0 here, a0 a0, which means a0 will remain, a1 and a1 bar opposite, so that will go. Okay, so this is why for a greater than b. So this is the final thing regarding the comparators. I hope you could understand the concepts. Thank you.